I'm desperate to teach people how this aircraft works, and I'm focusing purely on the ram air turbine. The ram air turbine, I've got 3 documents here, and I'm going to run through the 3 documents with you. The ram air turbine is deployed. When it's deployed, an amber unlocked light shows at the ram air turbine switch. The hydraulic function system monitors for conditions and sends data to the remote power distribution units to deploy the RAT with any of the following. In bold are the headings, not in bold are the descriptions. So you can see here, there's a bold and then a not bold. The bold means the high level, and the non-bold means the detail. Okay, so loss of all engines. Both engines less than minimum idle RPM. So that's a subset of that. And for some reason, this and many other documents put a line break there. They've made a mistake. Or they're trying to show you that it's loss of all engines primarily. So think of it like that. So in case someone says, oh, but that's by that. Doesn't matter. It will eventually deploy. So they're saying it's loss of all engines, and then they're putting on a different line item so that you don't focus too much on both engines being less than minimum idle RPM, because it will deploy. If the engines have failed, it will go below minimum idle RPM, so it's okay. Loss of hydraulic power, left, right, and center systems detect low pressure. Loss of electrical power, and that one is another line break, but that goes to the right of this picture, which is a pain, which is, so that loss of all electrical power is the bus power control units detect loss of power to the C1 and C2 transformer rectifier units. A rectifier unit is something which takes the higher, not necessarily higher, but in this case the higher alternating current voltage and turns it down to a lower DC current voltage, 28 volts direct current. Now, these TRUs, they have on the input, they have an electric load control unit controlling them with a current transformer current detection system, looking at current going into the C1 and C2 from the generators. On the output, they have a Hall effect sensor current sensor. That Hall effect current sensor would have sensed a ridiculous amount of load during the short circuit of the battery, and would have shut down the rectifier units, which meant that the incoming current would have turned off because it's no longer drawing power, which would have triggered the detection of loss of power into the C1 and C2 transformer rectifier units. Okay, so that's your third one. You've got 1, 2, 3. Let's just remember that. 1 is engines below minimum idle RPM. 2 is all the hydraulics under 2000 psi. That's the limit. And 3 is loss of the instrument buses. Just think of it like that. Okay, so let's look at another document. After quickly touching on the fact that the main battery or the APU battery can deploy, okay, so it needs one of those, can deploy the RAT. Main battery's broken, good thing it can accept it from the APU battery, like it started the APU with the door opening, okay? Alrighty, next document. They've done it correctly here. How much can it do? It can do this many, 5,000 psi of hydraulic power, can do 235 volts at 10 kVA. It's pretty damn good, actually. The generators that I muck with are like, 60 kVA and they're the size of a house. This is incredible. An internal governor changes the blade pitch to keep the constant blade speed so that it works like a turbine and makes the most of the air. Alright, it does have a minimum speed of 120 knots before it won't really work properly. Anyway, here's the conditions that cause the RAT to deploy. Once again, loss of all engines, both engines less than minimum idle RPM. Minimum idle RPM. Not pressure corrected N2, not safe idle at 11,000 feet. Minimum idle RPM. That's 50% N2 rotational speed. Rotational speed. 50% N2 rotational speed of the N2. Roughly. Then, okay, loss of hydraulics power, left, right, and center, detect low pressure. And then finally, loss of electrical power. The bus power control unit detects loss of all 6 generators. That's the same as we mentioned before. There's 4 variable frequency generators, or starter generators, 2 in each engine, and then 2 in the APU. And it's detecting that by nothing supplying the TRU, the C1 and C2 TRU. The only way that they would lose their power would be if it's lost all 6 generators. Okay, but that's silly, isn't it? Because we've managed to trick it by stopping the output of the TRU, because then there's no more current going into the TRU. That's a bit silly. So it's actually that it detects loss of power coming into the TRUs from all 6 generators. And then again, the same thing again, 2 independent power sources, main and main battery and APU battery. Next document. All right. More about the blades. Hydraulic power available in 6 seconds when it's out. Electrical power available in 10 seconds when it's out. Okay, once commanded. Okay, so now they've gone and done that same thing before. New line items, but they haven't got any bold. But then the same document, right? Loss of all electrical power. All right, and here's the description of that. BPCU detects loss of power to C1 and C2 transformer rectifier units. And then the same document, so that was in page 169. Now we're looking at page 180. Okay, the same document then lists it again as dual engine failure. All 3 hydraulic system pressures are low. Loss of the electric 28 volt standby bus. So that's the same again. 1, 2, 3. Forget about the during approach. Forgetting about the takeoff where the engine explodes. These engines didn't explode and pierce the cabin. That didn't happen. All right, and go down, go down, go down. And here they say it again properly. Here, the conditions that drive rack deployment include loss of all engines, indicated by both engines running below minimum idle RPM. Loss of all hydraulic power, left, right, and center systems detect low pressure, which is 2000 psi, or less than 2000 psi. And then loss of the electrical standby bus, which they seem to call electrical standby bus, which they mean 28 volt DC standby bus. All right. That last one, point 3, is why this rack deployed so fast. And let me show you why. This is the wiring diagram for just the left side. So that's the captain's instrument bus and the left common core resource cabinet, or the common computing system. That's the left so the captain's instrument bus is the left. First officer will be on the right. I'm showing you just the left. The right is a mirror of this. And then also below that, we have the hot battery bus. So here is the CCR cabinet left. CCR cabinet left's power inputs are displayed here. 28 volt DC, 28 volt DC hot battery bus into power conditioning module B and power conditioning module A. So this is left, 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 left. There would be a whole other cabinet with right, 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 right. Or right, right, battery, battery. Now, this is the main hot battery bus. This is the captain's instrument bus. Let's just start with the captain's instrument bus. See the 50 amp breaker there? That's a thermal breaker. Going down to common computing resource cabinet left, primary. The primary is the instrument bus. And guess where the secondary is? It's on the battery bus. So therefore, my failure scenario of losing the main hot battery bus shorting and then that bringing down the captain's instrument bus means your common computing resource cabinet is offline. Oh dear, that's terrible. So what do you lose? You lose, does anybody recognize something? Landing gear indication and control? I wonder why the gear didn't continue to retract. You lose hydraulic system control. I wonder why the gear didn't continue to retract. And you lose electrical power distribution and control. You've lost all of this. The airplane is lucky to be in the air. Good thing the flight control computers, the FCEs, right? Good thing they have their own internal batteries. They had some chance of pulling up and clearing that building. That's just incredible how well he did to nearly clear that building. Okay, it's just incredibly good effort. Unfortunately, it's just too tall. Okay, so when you lose that, what happens? So here is from Hamilton Sundstrand. This is the company that designed and manufactured the ram air turbine and the entire power distribution system for the 787, and this is the document about it. Electrical power generation system. Aircraft standby operating mode, which is, if you can read up above from the same document, bus power control unit right, standby mode rack deploy. Okay, that's what it is. So the normal operations would entail a 15-second countdown. And that's to make sure it doesn't deploy the rat unless it absolutely has to. That's because the rat is a gigantic aerodynamic drag. And so it wants to make sure that it doesn't do that unless it really needs to. So it counts down 15 seconds and monitors that. The only way that it wouldn't do that is if it has been commanded by any of the things we mentioned before, the ram air turbine control breaker auxiliary contacts have closed, the 15 seconds should have counted down, but there is none of these commanded on. So let's look at this logic gate. The rounded logic gate is an OR gate. A flat one is an AND. A line directly in means is, and a line with a dot at the end like that means is not. So this will go straight through to bypass the 15 seconds in the following circumstances. Rat control breaker is commanded on. One of those triggers. Okay, and is not live from this input. This input would be live if any of these were on. Okay, all of these have lost their command, their actual command signals, because the command is dead. The command is offline. All of this computer is gone. So therefore, any VFSG? No. Any APU starter generator? No. Any forward EP commanded on? No. So therefore, no is correct. That is correct. Bypass 15-second countdown. Deploy rat immediately. Bam. So now you understand. It is physically impossible for that ram air turbine to have been out when it was. Physically impossible.